Welcome to an Atlas instructional video on modules. This is a feature of the software which provides improved handling of irreducible and standard modules and virtual characters in the basis of irreducibles and also the basis of standards. I'm going to assume some familiarity with the software, in particular the RealX interpreter version of the software. So I'm going to assume that you've installed this on your system and you know how to run it, and you've played with the software a little bit and are familiar with it. So I'm going to start the software here as I usually do. From the command line, you give the command RealX, and it starts up and it tells you a little bit of information about what version it's running. And then the first thing I always do is I load in a bunch of auxiliary files which have a bunch of extra functions which I'm interested in using. I've combined all of them into a single file called my, and so I just need to load this one file which is my.rx. And when you read in this file, you see it defines a whole bunch of functions, and it tells you what it's defined along the way. And along the way, it also is loading in these other files. For example, it loaded the Hermitian.rx file and unitary.rx. And at the end here, it said it was completely done. So I've read in the my file and all of these subsidiary files and all of these definitions. Now today I'm going to be concentrating on another file, the file coherence.rx. So I'm going to load that in separately. And that has a bunch of definitions related to coherence, continuation, and translation functors and such. And you can see here what's been read in. So now let's start with a very basic example as usual. Let's take G to be the group SL2R. And let's take everyone's favorite parameter, which is the trivial parameter for SL2R. T is trivial. And so as it says here, T is a parameter, and let's look what it is. It's described by this triple x lambda and nu, and this is should be familiar to everybody who's watching this video. These are parameters from the Atlas software, and this parameter comes in a block, which I'm printing here. This is a block of 3 parameters, or 3 representations. They're labeled 0, 1, and 2, and they correspond to the 2 discrete series in the trivial representation. And so far this is standard Atlas stuff. There's nothing new yet. Now what I want to emphasize is that until now the software only had one kind of object along these lines, and these were parameters. And a parameter would be interpreted as either a standard module or an irreducible, depending on the context. So let me illustrate that with an example. You can ask for the composition series of a standard module. So you say composition series of the parameter T. And the software from the context knows to interpret T as a standard module. And what it returns is a list. And it's a list of 3 modules, each with multiplicity 1, plus 1. And these are, again, by context, interpreted as irreducible representations, each of which is occurring with multiplicity 1 in the composition series of this standard module. On the other hand, you can ask for the character formula of an irreducible representation. You say character formula of the parameter T, and by the context, you interpret T as an irreducible representation, and it returns a linear combination with signs of these 3 parameters, which are now viewed as standard modules, and this is the formal expression of an irreducible representation as a linear combination of standard modules. So both on the input and on the output side, you need to know the context to understand how to interpret these parameters. What's new with the modules feature of the software are utilities to help to understand and delineate the distinctions between these different kinds of objects. So let's look at that. So let's remind ourselves we have this parameter T, and now there's a new object called J of T. J stands for irreducible. And J of T is what it means is the parameter T viewed as an irreducible representation, in this case the trivial representation. And you see that what j of t is it's precisely the parameter t with this additional flag, which is just a string IRR to specify the fact that it's being viewed as an irreducible. And on the other hand, the standard modules are denoted I. I is intended to indicate induced representation. I of t is the standard module parameterized by this parameter. In this case, it's the reducible principal series. And now this, as an object in the software, is again a pair of the same parameter with a string, and now the string is std to indicate this is a standard module. So there are three sets which are in bijection: parameters, irreducible modules, and standard modules. Now there's a new command called mprint. So let's look at that here. If you do mprint of a standard module such as I of t, what you get is I of the parameter, indicating this is the standard module associated to this parameter. And similarly, j of t is j of this parameter, and that's how irreducibles and standards are indicated. So for example, if you use mprint to look at the composition series of I of t, what you get is the sum of three irreducibles with multiplicity 1, and now these j's here are indicating that these are the irreducible representations with these parameters. And similarly, if you use mprint to look at the character formula of j of t, what you see is you're getting a linear combination with some plus and minus 1s of the standard modules now, which are indicated by I. So there's a lot of new information here. On the output side, it's telling you whether these modules are standards or irreducibles. And also on the input side, it's important to keep the I and the j straight. And so, for example, if you asked for the composition series of j of t, the software would complain because certainly you don't mean to ask for the composition series of an irreducible module. And similarly, one should never ask for the character formula of a standard, and the software will reject that also. I'd like to look some more at this SL2 example, and so I'm going to give some new names to some objects. So let's set B to be this block we've been talking about, the trivial block of SL2. And I want to use all three parameters now, not just the second one. So I'm going to let P0 be the 0th parameter, P1 and P2 be the three parameters in this block. So let's look at them. P0, P1, and P2 are these three parameters we've seen already, two discrete series and one principal series. And I also want to look at the corresponding irreducible modules, J, so let's call J0 J of P0. And similarly, j of 1 and j of 2. And that's the three corresponding irreducible representations, two discrete series, and the trivial. And finally, let's give names to the three standard modules. I0, I1, and I2 will be the three corresponding standard modules. I have P0, I have P1, and I have P2. Okay, so that's just some convenient names for things. And so now I can look at a couple of other examples of some of these operations. So first, let's just remind ourselves, do again something we did a minute ago. Let's look at the composition series of this standard module I2. And as before, we see that it's the sum of three irreducible representations in the Grothendieck group. And now let's look at the composition series of this standard module I0. We see that it's just the single irreducible J0. That is to say, the standard module and the irreducible module are the same, and the discrete series can be viewed either as an irreducible or a standard. Now, there's another capability I'd like to demonstrate now, which is that J0 plus J1 plus J2 is equal to I2. So I'm just going to enter that expression, and the software returns true. So that is to say, it handles operations in the growth and group, and this is just another way of expressing what what's several lines above. Now let's look at this a little bit further. This expression that I have, J0 plus J1 plus J2 is equal to I2. On the left-hand side, it's a sum of three irreducibles. And on the right-hand side, it's a standard module. But when presented with such an equality of objects, the software computes the composition series of the standard module, and now it's comparing these two sums of irreducibles and sees that they're the same. I should mention that this is one place where the software is implicitly doing some type conversions, and there are a number of places in which this happens. And there are a couple of places where this can be tricky. I'll illustrate a few of them later. But let me just say that in situations where either the software is doing type conversions or the user is doing type conversions, there are situations in which some care is necessary. Okay, so let's look at this operation again of taking composition series and character formulas. Well, these are actually inverse operations. They can be applied to virtual characters. And so if you take the character formula of the composition series of something, excuse me, that was a misprint, you get back the original module. And similarly, if you take the composition series of the character formula, you get back the original irreducible. So you should really think of these two functions as being change of basis matrices between on the space of virtual characters between the basis of irreducibles and standards. Let's go back to this I0, which is the discrete series standard module, and as we saw before, the composition series of it is the single discrete series. And similarly, the character formula of that single discrete series is just the single standard module. And so, as I mentioned above, really in the growth and group, I0 and J0 are equal to each other. They're both discrete series representations from a different point of view. But if you say I0 is equal to J0, the software will complain. And the reason is that probably this isn't the question that you wanted to ask. The question really makes sense in the growth and group. And although the software could automatically convert to the growth and group, it doesn't. It raises a flag. But if you really did want to do this comparison, it gives you a tip. You could say, ask whether virtual of I0 is equal to virtual of J0. And what virtual does is it's an explicit type conversion from a standard or irreducible module to an object of the growth and group. And as virtual modules, these two objects are equal. So let's just look and see what this virtual operation does. This thing I0 is a parameter together with a string std, and virtual of I0 is 1 times the same thing. This is an example of a situation where some care is necessary when doing type conversions. Let's look at a few more examples of the basic modules constructions. I'll take G to be the group SP4R, and let's take T to be the trivial parameter, that is to say trivial of G. And let's take a look at what T looks like. So T is a triple again. And now lambda is 2, 1, which is rho for this group. And the first thing we should do is look at the block of the trivial representation. So that is to say, let's do a print block of this parameter. And this is a block of 12 representations labeled 0 through 11. The trivial parameter is number 10. And just to warm up, let's do the same example we did before. Let's look at the character formula of the trivial representation J of t. So here it is. It's a linear combination with signs of these standard modules, and all but one of them from the block occur. And this is an example of the Zuckerman character formula for the trivial representation. Next, let's look at an example of writing a loop to look at the composition factors of all of the standard modules in this block. So I'm going to write a for loop for P in B. B is the block, do. The first thing is just to print a carriage return. And then I want to do mprint of the module, I of P. And then mprint of the composition series of the module. And terminate all of that with an OD for the end of the loop. And semicolon at the end to suppress any extra printing. And this will run over the block and print the composition series of each standard module. So let's go back up to the top and look. Here's the first representation. The standard module I is right here, and it's got a composition series of length 1. That's a discrete series. And these first 4 are the discrete series. And the next one in the list is a standard module with a composition series of length 3. And so on down towards the end of the block. The composition series get longer as you go. And in this case, the trivial representation is here. This is the standard module containing the trivial. And notice, for example, that it has a fact coefficient here of 2, an irreducible which occurs with multiplicity 2. Let's move on now to the translation principle. I'm going to start with formal translation of parameters. This is a way of obtaining new parameters from old and is closely related to Zuckerman's tensoring with finite dimensionals functor. So let's illustrate it by starting with our favorite group SL2. And let's start with a discrete series parameter for SL2, and I'm going to define it by this command, large discrete series of G. This is a new command. When G has large discrete series, this gives you one of them. And let's check this parameter is this fellow right here, which we've seen before. And let's check that indeed it is a discrete series representation. This virtual, this standard module is irreducible. And let's check what the infinitesimal character of this parameter is. Well, of course, that's the infinitesimal character command. And the answer is 1. Now, what coordinates are we using? Well, let's check. Rho of G tells you what rho of G is in these Atlas coordinates, and in this case, it's 1. So the coordinates that Atlas is using may or may not be what you're familiar with. So rho of G is helpful in determining how the coordinates are working. Now here's the new command. I'm going to set Q to be the translate to applied to P, and it's going to translate the parameter P to the new infinitesimal character 2. And here it is. It looks just like the old parameter, except that lambda has changed from 1 to 2. And the infinitesimal character of Q is now 2. This is the next discrete series up, the next one out into the dominant chamber. And it is indeed a discrete series representation. Its standard module is irreducible. Let's look at another kind of translation. Let's do, let's set Q to be translate by, and I give the command translate by, and here I'm going to use the argument as 1, and this is going to shift the infinitesimal character by 1. So this gives exactly the same result as what I just wrote. It's going to change infinitesimal character 1 to infinitesimal character 2. And I check that, in fact, these Q is equal to R. This has the same effect. I usually use the translate to command. Okay, let's do another example. Let's do translate to 0. Let's see what we get. Here's Q. It's a final parameter, and it looks the same. Now lambda has been replaced with 0. And this is the infinitesimal character of this parameter is naturally 0. This is a limit of discrete series. And once again, I'll just check that the corresponding standard module is still irreducible. Okay, I'm going to go one step further now. Let's do the following. Let's set Q to be the translation of this parameter to the point -1. Now, this is a little bit tricky. -1 is not in the dominant chamber. And nevertheless, this is something you can do. However, if you ask about this parameter, it says it's a non-standard parameter. So that's because this lambda is outside of the dominant chamber. And so, formally speaking, this is a perfectly well-defined object. Its infinitesimal character is -1, which is equal to 1 in the Weyl group. But nevertheless, there's a parameter defined with lambda is -1. The Atlas software doesn't currently make any use of these parameters, but formally speaking, it's perfectly well defined. However, you cannot take I or J of a non-standard parameter. Okay, let's continue by looking at the principal series parameter and translating that. So let's take T to be the trivial parameter of SL2. And of course, we know what this parameter is. We've seen it many times. It has infinitesimal character 1, which is to say rho. And we can translate it just as we did the discrete series. We can translate this parameter to infinitesimal character 2 using the translate to command. And let's see what we get when we do that. So the parameter Q should look pretty similar to the parameter T. And of course it has the same X, and nu has changed from 1 to 2 in this case. And lambda has also changed from 1 to 2. And the way lambda and nu work under these translation functors is in general pretty complicated. But in any event, that's what happens in this example. And the main point is that this new representation is supposed to be essentially the same as the old one. In particular, it's supposed to have the same kind of composition series. So the standard module we started with, I of t, has a composition series of length 3, 2 discrete series plus the trivial representation. This new parameter has something very similar. It's 2 discrete series plus a finite dimensional, all going on at infinitesimal character 2. All right, let's go in the other direction. Let's translate this parameter to 0. So let's do translate to 0. And something interesting happens now. This parameter that I get is a non-final parameter. So I'm not going to get into the details of these different kinds of conditions, but non-final is a condition on a parameter. The final condition is what tells you that this standard module has a unique irreducible quotient, and this particular example fails that. It's still a perfectly good parameter. You can define I of R, and it's just this parameter I of R. But if you look at J of R, then you'll get an error. And a non-final parameter, this module does not have a unique irreducible sub or quotient. And so J of R is not a valid operation. So let's look a little bit more at this example. The point is that this module. Oh, so I'm just mentioning here in writing the fact that this operation J of P is only defined for final parameters. I of P is okay for non-final. And let's look at our particular example. If we look at this virtual module that I have, I of R, that's a misprint. I said I of P, and that's not defined. But I meant to say I of R. And if we look at this virtual module, we see that it's the sum of two discrete series, actually, excuse me, limits of discrete series. This x equals 0 and x equals 1 with lambda is equal to 0. These are the two limits of discrete series. This induced representation is the direct sum of two limits of discrete series. And really the direct sum, not just in the Grothendieck group, which is to say this module does not have a unique irreducible sub or quotient. Okay, let's go one step further. Let's look at the translation of this parameter to the point -1. So let's set z to be this translate to the point -1. And as before, this is a perfectly well-defined parameter. In the case of the discrete series, we saw that this was a non-standard parameter. And if we look at it, in this case, what do we see? It's rather interesting. This is a perfectly good final parameter. So that's a subject for another day, but I'll just say that in this example, it is possible to move to a point not in the dominant chamber and get a perfectly good final parameter. Let me conclude this discussion of translation of parameters by constructing the irreducible principal series at infinitesimal character rho of a split group. So the basic idea is that it's easy to construct the irreducible principal series at 0. That's the spherical one. So with G is equal to SL2, let's set P to be the spherical principal series of G at 0. So this spherical principal series is a new command, and it does exactly what you think. It gives you the parameter of the spherical principal series at that infinitesimal character. And so let's look at this parameter I of P. There it is. And let's look at its composition series. It consists of just a single term, J of P. That is to say, this is indeed the irreducible spherical principal series at infinitesimal character 0. So that was easy to construct, and now the idea is to construct the irreducible one at rho. You just translate it, this guy, to rho. So let's set Q to be the translate to of P to the infinitesimal character rho. And let's see, this parameter is, in fact, the composition series is trivial. That is to say, this is an irreducible representation. And let's look at this parameter, I of Q. Here you see that nu is equal to 1. That's clear for a principal series. That's the infinitesimal character. This lambda is a little bit more obscure in the case of a principal series. I'm not going to get into an explanation of what it is here. I'll just say it has something to do with determining the character on M, the Z2, the product of a bunch of Z2s. So let's show the power of this operation by doing the same thing for E8. So let's take G to be the split group of type E8. And let's set P to be the spherical principal series parameter for G. at the point at infinitesimal character 0. Okay, let's give it a second to compute. Now let's check. Let's look at this parameter I of p. It's a rather interesting parameter. The first entry, this x, which I haven't really explained, is 320,205. And lambda is rho, and nu is 0. And let's look at the composition series of this representation. This takes a few seconds to compute. But there it is. This representation is indeed irreducible. And now let's translate it to rho to get the irreducible principal series at rho. I can simply put rho in for the second term there. And let's check. This new parameter that I'm getting, I of q, is the same as the old one, except that you've changed both lambda and nu. Nu is now rho. Let's check. Rho of g is 1 in these coordinates. And finally, let's just check the composition series of this fellow. And indeed, after a few moments, it will tell us that this is irreducible. Let me conclude this discussion of translation of parameters with this comment. The translation of parameters is primarily intended as a method of obtaining new representations similar to old ones by varying the infinitesimal character. And almost always one should think about doing that within the given file chamber or perhaps in its closure. We turn now to the translation principle in the setting of modules. The idea here is similar to that of parameters. It is a tool for producing new modules, irreducible or standard, from old ones, and the technique is to use Zuckerman's translation functors, which are obtained by tensoring with a finite dimensional and projecting on an infinitesimal character. The principle here is that this operation is very nicely behaved as long as one stays within a given file chamber or at worst is passing to the closure of it. So I've stated that here. The Zuckerman functors, which are tensoring with a finite dimensional and projecting on an infinitesimal character, take irreducibles to irreducibles and standards to standards as long as one stays within a given chamber or goes from a given file chamber to its closure. And that's what we're going to be working with mainly. So let's look at some examples. Let's take G to be SL2. And let's start with the large discrete series parameter. And now we're going to be talking about modules, so let's let pi be j of that parameter. Let's look at this this parameter, this representation pi is an irreducible representation, the discrete series at rho. And we've already seen how to translate the parameter to rho, which is to say 2. This is what we saw before. And what's new now is you can apply this operation to the irreducible. You do translate 2 applied to pi, and what we get is the irreducible discrete series at 2, which is to say that the translation of irreducibles commutes with the translation of parameters, which is to say that the translation to pi the translation of pi to 2 is the translation of the parameter to 2, and it's j of that. So there's not much new there. This is just what we saw before on the level of, now it's on the level of these irreducibles. Let's set LDS be the translation to 0 of this irreducible. LDS stands for limit of discrete series. This is a perfectly good irreducible representation at infinitesimal character 0. Now, there's a couple of subtleties about going to infinitesimal character 0. Let's check. The infinitesimal character of this representation is indeed 0. And first I want to illustrate that if you, first you cannot translate pi to -1. Even though this operation is well defined on the level of parameters, on the level of representations, this is not allowed. And another thing that's not allowed is if you start with this limit of discrete series at infinitesimal character 0 and try and translate it out to rho, this is not allowed. Because you're allowed to go from a point to a more singular point, but not from a more singular point to a less singular. And that is to say, I'll summarize it here, translation of modules to non-dominant parameters is not allowed. And translation of modules, so to speak, away from walls is not allowed. Away from a root wall is not allowed, because that doesn't give you an irreducible. It doesn't take an irreducible to an irreducible. Later, we're going to discuss translation on the level of virtual modules, in which case this will be allowed, but that's not what we're talking about here. Now, translation from regular to singular infinitesimal character is a very important operation, so there's a special functor for this called the psi functor. This dates back to Zuckerman's original paper. And the idea is to specify a set of walls to translate to. So let's look at our example of our discrete series of SL2. And we've already seen how to translate that to infinitesimal character 0. And now we have a new way of doing that, which is to say, apply the functor psi to pi, and the argument 0 means 0 refers to the 0th simple root, and this says translate pi to an infinitesimal character which is singular on that one root, on the 0th simple root wall. So that's exactly what translate to did. It's just a shorthand for that. And that operation takes irreducibles to irreducibles, or 0. Let's look at a slightly bigger example where we have more than one root. Let's take the large discrete series of SP4, and there it is. Let's translate that to the 0th root wall. So that is to say, psi of pi to root 0. And what you get is this parameter for a limit of discrete series. You see that lambda is now 1, 1. And so let's just double check the infinitesimal character of this representation is indeed 1, 1, which is singular on the root E1 minus E2. Similarly, if you translate to root number 1, you get infinitesimal character 1, 0, which is singular on the root 2E2. And you can translate to more than one root wall. You have a set of root walls given by an array like this, 0 and 1. And in this case, that's both simple roots. So this is giving you the translation of this large discrete series all the way to infinitesimal character 0. Let's go back to the SL2R case and look at the trivial parameter. And let me just look at a couple of examples of psi in this setting. So you can apply psi to the parameter itself to get this non-final parameter that we've seen before. And you can apply the psi functor to the corresponding standard module, and you're getting the standard module, non-final standard module at infinitesimal character 0. On the other hand, you cannot apply the psi functor to the irreducible because that's 0. That is to say, this is the trivial representation, and if you translate the trivial representation to 0, the module vanishes. And again, later we'll see a way to do this in the setting of virtual modules. But just strictly in terms of irreducibles, this is an operation which doesn't give you a new irreducible. It's time now to look at the translation principle where it really belongs, which is in the setting of virtual modules. So let's take G to be SL2, and let's take pi to be the trivial irreducible representation. And let's take capital P to be the corresponding element of the Grothendieck group, the virtual module corresponding to pi. So let me remind you that pi itself is an irreducible representation, whereas capital P is the virtual module 1 times that. And we've already seen, of course, how to translate this representation pi to infinitesimal character 2. This is the two-dimensional irreducible. And, well, what's new now is that we can also do this on the level of virtual modules. And in this case, of course, what you get is exactly 1 times the finite dimensional. Now, where things diverge is when you look at singular infinitesimal character. If you try and translate pi to 0 as an irreducible representation, the software will complain. But the translation of the corresponding virtual module is well defined. It's the empty sum of standard modules. And if you apply mprint to this thing, you will see that you get nothing. But at least it didn't give you an error. It's a perfectly well-defined object in the setting of virtual modules. And to look at another example of this sort of thing, let's let Q be the composition series of the standard module, the trivial standard module, which is to say this reducible principal series at rho. So let's remind ourselves Q is the sum of 3 irreducible representations, 2 discrete series, and the trivial representation. Now if you translate this to infinitesimal character 0 to the wall using the psi functor, what happens? Well, these 2 discrete series survive and the trivial representation dies. And so what you get is the sum of the 2 limits of discrete series, each with multiplicity 1. And something that's worth checking, I suppose, is that this agrees with the psi functor applied to the corresponding standard module. So you apply psi to the standard module I of the trivial parameter and translate that to the 0 root wall. And these 2 things are equal. And this is an example of a type conversion. The left-hand side is a virtual module, and the right-hand side is a standard module. And the software assumes that you want to check whether these are equal in the Grothendieck group. We next look at the very important functors for translating away from a wall. These are called the phi functors, again following Zuckerman's terminology. And you start with a representation with singular infinitesimal character, and you apply a translation functor tensoring with a finite dimensional and projecting, and you get a representation typically reducible, or a virtual representation at regular infinitesimal character. So let's look at an example. Let's start with our favorite example, the large discrete series for SL2. This is that infinitesimal character rho. Now let's translate it to the zero root wall to make it have singular infinitesimal character. So, and we've seen that's the limit of discrete series. So let's call it that. Let's let LDS be the translation of the discrete series to the zero root wall. This has singular infinitesimal character. Now, we can't translate this out as a representation, but we can as a virtual module. And that's accomplished by the phi functor. We're going to translate back from 0 to rho in this example. And so the functor that we apply is called phi. It's called phi. And the syntax is the following. You apply phi to the representation you're interested in. 0 indicates the root wall, and 1 indicates the infinitesimal character you're translating to. You're translating away from the wall, but you need to specify in addition which infinitesimal character you want to land at. And we see here what we get is a virtual module, which is the sum of two copies of the discrete series plus a copy of the trivial representation. So this is just a virtual module. It's certainly not irreducible. And what it says is that the limit of discrete series, when you apply this phi functor to it, what you get is 2 times a single discrete series plus a single copy of the trivial representation. So this is our first example of a rather subtle translation functor taking an irreducible to this linear combination of irreducibles, with one of them with multiplicity 2. So let's do a little experiment. Let's let I be the standard module of the large discrete series parameter. So that is to say, this is the same representation as the discrete series itself, but viewed as a standard module. And I'm just going to check in the Grothendieck group, pi and I are the same. And of course we can apply these functors in the basis of standard modules. So let's let I sing be the standard module with singular infinitesimal character obtained by translating I to the 0 root wall. And let's look at this fellow. And of course, this is the same representation as the limit of discrete series viewed as a standard module. So now let's apply phi to this representation. And what I'm going to get is a linear combination of standard modules, since I've given you a standard module. And here it is. It's a linear combination with signs of these 3 standard modules, the 2 discrete series and the reducible principal series. It's the reducible principal series minus 1 discrete series plus another. So of course this linear combination of irreducibles and this linear combination of standards are clearly supposed to be equal in the Grothendieck group. So let's check that. So the question is if phi of this singular standard module is the same as phi of this singular irreducible. And since the irreducible and the standard are equal, then when you apply phi, of course, what you're getting is equal. And surely the answer will be true. This operation of starting at regular infinitesimal character and translating to a simple root wall and then back out again is sufficiently important that it gets its own name. So let's look at an example. Let's start with a discrete series of SL2 at rho and translate to the 0 wall and then back out again. So you first apply psi and then you apply phi. And when you compose these, you get this thing that we've just seen, this linear combination of two irreducibles, one with multiplicity 2. And we combine these two operations in a single functor called phi underscore psi. And so you apply phi underscore psi to pi, and you specify the root 0, and we get exactly what we just computed. Now, it's not necessary to specify the target infinitesimal character when you do it this way, because you started at regular infinitesimal character, you pass to a wall, and by definition you're going back to the original infinitesimal character. So there are only two arguments, the representation and the integer specifying the simple root. Let's look at one other example. Let's let I be the standard module, which is the principal series for the given by the trivial parameter, and let's look at what phi psi of this is. Well, you take this and you translate it to the wall, and you translate back out, and it turns out that you get 2 times the original standard module. That's interesting. Let's just check that that's really what I got. The claim is that phi psi of I is equal to 2 times I. And we simply check that, and it's true. We turn now to the important topic of coherent families and coherent continuation. The setting is entirely that of virtual modules. So we're going to start with a virtual module with infinitesimal character lambda, and what we get from that is the coherent family defined by pi, which is a map from the set lambda plus x upper star, this translated lattice, to the space of virtual characters, and associated to an element gamma of that set is a virtual character of infinitesimal character gamma. So let's look at a simple example. Let's start with the discrete series of SL2. And let's just check the infinitesimal character of this representation, of course, is 1, which is to say rho. And the syntax is the following. I'm going to set C to be the coherent family of pi. Okay, so the command is coherent underscore family, and it's applied to a module, which will be interpreted as a virtual module. And now this is something a little bit new. What we get is a map or a function which takes a ratvex, which is to say a rational vector, and returns a pair consisting of a virtual module and a string giving, say, irreducible or standard. It's often useful to use the what type command, and I'll use that here. It gives the same information. It says this C that I've defined is a function from rational vectors to pairs. So for example, let's look at, you take this coherent family and you evaluate it at the point 1, and of course what you get back is the original module, and of course it's interpreted as a virtual module, so it's 1 times the original irreducible. So a coherent family at the original point is the module that you gave. And I'm just checking that this is true. And just a little reminder here, this is an example of type conversion. The left-hand side is a virtual module, which is a parampole. And the right-hand side is an irreducible module. And the software, if you ask for the equality of 2 such things, the software reasonably interprets the question as to being 1 in the Grothendieck group and converts the right-hand side to a virtual module and checks equality there. Okay, so let's look at this coherent family evaluated at a different point. What is its value at 2? Well, what that is the discrete series with infinitesimal character 2. And let's just check. The infinitesimal character of this representation is indeed 2. And what this representation is simply the translation of the original discrete series from rho to 2. And within the dominant chamber, that's what coherent families do. They just give you they agree with these translation functors. And that's even true when you go from the interior of a chamber to something singular. The coherent family at 0, this is a common mistake to forget the parentheses here. The coherent family at 0 is the limit of discrete series. And indeed, that is the same thing as taking the original representation and applying the psi functor to it to translate it to the wall. Let's check that. C of 0 is indeed equal to psi of pi to the 0 root wall. Okay, now this is where things get interesting. Let's set Q to be the coherent family at the point -1. And this is the first time something interesting is going to happen looking at a parameter outside the dominant chamber. This is allowed, even recommended, when you're talking about coherent families. This is largely what makes them interesting. So we're looking at this coherent family at -1. So I called it Q because it's a virtual module, and there it is. It's the sum of the discrete series and the trivial representation, both of those irreducibles denoted by J, and the infinitesimal character is 1. Well, the infinitesimal character, according to what I said earlier, is -1, but in the Wahl group, -1, if you make it dominant, it's 1, so that's correct. So the coherent family in this example, the virtual modules that you get at 1 and -1 both have the same infinitesimal character, which is to say rho. Okay, let's look at another example. Let's look at the value of this coherent family at the point -2. Let's call that R. Well, let's check something. Well, first let's check its infinitesimal character, and of course it's -2, which is the same thing as 2. So let's check something here. Suppose I take this Q, which I obtained by coherently continuing from 1 to -1, and then translate to 2. Well, the way you think of that is you go from 1 to -1 to -2, and that's exactly what R is. It's the value of the coherent family at -2. All right, let's look at another example here. Let's take pi to be the trivial representation, J of the trivial parameter. Okay, let's look at pi as the trivial representation of SL2. And let's take its coherent family. We'll take C to be the coherent family of pi. Okay, and let's look at what is C of 0, the coherent family at parameter infinitesimal character 0. Well, that's empty. That's exactly correct. The trivial representation, when you translate it to 0, you get the empty virtual module. If you look at m print of psi of this thing, you get the same thing. If you want to reassure yourself, you can look at psi itself. Look at psi of virtual of pi to 0, and you see it's the empty sum of standard modules. So the trivial representation translated to 0 is empty. And now let's look at the coherent continuation action. Let's set P to be the value of this coherent family at -1. And let's look at it. And what we get is, interestingly, minus j of this parameter, which is to say minus the trivial representation. So when you apply coherent continuation to the trivial representation, you get minus the trivial representation, as I've checked here. Okay, let's look at another example. Let's take I to be the reducible principal series, I of the trivial parameter. And let's look at the coherent family of this representation. Let's take the coherent family of I and evaluate it at -1. Now, that's a common mistake right there. I always forget that extra set of parentheses that I need. So let's get that right. Let's take, we need those extra parentheses right there. And when you look at -1, you see that I goes to itself. The standard module, when you apply, when you look at it at -1, it goes to itself. So let's just check that. The coherent family of I evaluated at -1 is, in fact, I. Okay, we're going to turn now from coherent families to coherent continuation. So coherent continuation is an action of the Weil group on the space of virtual modules. And it's defined as follows. If you have a virtual module pi with infinitesimal character lambda, then w dot pi is by definition the coherent family of pi evaluated at the point w lambda. And actually, to be precise, w has to be in the integral Weil group of lambda. Let's take the coherent family of this. This is what we've been looking at. And again, we can look at the value of this coherent family at -1. And the new command is the command coherent. And you apply this, the first argument is an integer giving a simple root, and the second argument is your virtual module. So this is giving the action of the 0th simple root on pi. And let's look at it using imprint as usual. And we see this is exactly what we just wrote, the value of this coherent family at -1. Okay, so this defines the Weil group action one simple root at a time. So for example, you can compose two of these. We can apply this coherent continuation action twice to pi, and fortunately we get back exactly pi itself. 1 times pi, of course. It's a virtual module. And let's check one of these identities. If you take the coherent continuation action through simple root 0 and then translate to infinitesimal character 2, that's exactly the same thing as evaluating your coherent family at the point -2. I checked this identity earlier. This is checking it with the coherent continuation action written in terms of the Weil group. And it's worth checking another identity, which is you can do things in the other order. If you take your parameter and you translate it within the dominant chamber from 1 to 2, and then apply the coherent continuation action, that gives the same thing. Let's look at the relationship between the coherent continuation action and this phi psi functor. Let's look at the coherent continuation action of the simple root on the discrete series of SL2. We saw that what you get is the discrete series plus the trivial representation. And that may look familiar because if we apply phi psi to this representation, we translate it to the wall and then back out again, we get something very similar, except the first coefficient is 2. So that says that, at least in this example, if you take phi psi of pi, if you take the coherent continuation action of pi and add pi to it, what you get is the phi psi functor applied to pi. And that is an important general identity. The coherent continuation action of a simple root is plus 1, plus the identity is equal to phi psi. So let's look at a couple other examples of this. Let's take pi to be the trivial representation. So let's look at this identity in the case of the trivial representation. If you apply coherent continuation in the simple root applied to pi and add pi, what you get is phi psi applied to pi. That's true. Well, let's unpack this a little bit. The left-hand side, the coherent continuation of pi is, we saw, minus itself. So if you take that and add it to itself, you get empty. And if you look at phi psi of the virtual representation pi, that's what you get. It's 0, the empty sum of standard modules. And that's because when you apply psi to the trivial representation, you get the empty virtual module. And by the way, that's why I had to use virtual pi instead of just pi here, because I wanted to apply psi to it and get the empty virtual module. Okay, so let's conclude by looking at a bigger example where we have two different roots. Let's take G to be SP4, and let's look at the large discrete series of SP4. So here's this parameter, here's this representation pi. Its infinitesimal character is 2, 1. And of course, it's worth checking that that's rho. Okay, so good. Now, we have two roots, 0 and 1. 0 is short and 1 is long. Let's start by defining the coherent family of pi, as usual. And let's see, for our first attempt, let's look at the coherent family evaluated at the point 2 minus 1. And we see that what we get is the sum of two irreducibles, discrete series and one other. And that's the same thing as the coherent continuation action of root 1 on pi. So let's look at that. And it's helpful to have a few tools at our disposal for looking at this Weilgroup action. So in particular, we can look at the matrix of the simple reflection of a given root. And this is in the whatever coordinates Atlas is using, and we can apply that to rho of G by multiplying it like this. And so we see that the simple reflection applied to rho is indeed 2 minus 1. So that's good. Let's look at the other simple reflection, 0. That's the short root. Let's look at the coherent family evaluated at the point 1, 2, and check that indeed that is the action, the coherent continuation action of root 0 on this representation. That is correct. And let's look at the Weilgroup also. Let's look at the simple reflection 1 applied to rho. Simple reflection 0 applied to rho. and see that we're getting the right thing. Indeed. Okay, so now we can compose these two different roots. So let's look at Q. Let's set Q to be the coherent continuation action of root 0 applied to the action of root 1, the composition of these two in this order. Okay, so this is a virtual module, and here it is. It has 5 terms, and notice that the x's are 0, 2, 4, 5, and 7. And of course, you don't need to write things out this way. You can do the action of a Weyl group element by writing it as a string like this. And we see the Q could be written as coherent 0, 1. Just to illustrate things a little bit, you could set W to be this Weyl group element 0, 1, and simply write coherent continuation action of W on pi. And that's what we're seeing here. Now let's check, this is the coherent family evaluated at what point? Well, here's the computation. You take rho and apply simple reflection 1 followed by simple reflection 0. That's the right order. And let's see what we get. Well, we get an error because I forgot a parentheses, but once you fix that, we see that we get -1, 2. So according to the description of coherent continuation, this Q that I have should be the coherent family evaluated at this point, -1, 2. And that's correct. So I'll conclude with just a couple more calculations along these lines. Let's take W to be the long element of the Weyl group. That is to say 0, 1, 0, 1. And let's look at the coherent continuation action of this element on the large discrete series of SP4. And what we see is we get this virtual module with 7 terms. And according to our description, this should be the coherent family evaluated at the point -1, -2. So let's check that. So we see that these two things do indeed agree. And for one final check of the software, let's compute the action of W squared, which is to say, let's take W to be this element, which according to the braid relations is the identity. And if we're lucky, when we apply the coherent continuation action of this element to the discrete series, we will get the discrete series itself back again. And with that final check, I will conclude this lecture.